Welcome back for this notebook on linear algebra. Full disclaimer, this is no substitute for a proper linear algebra class. As a matter of fact, this is no proper substitute even for what's in the appendix of the D2L book, but at least it'll get you started. So for all intents and purposes, this will teach you a little bit more on how to deal with tensors, vectors, matrices, norms, and so on in the context of PyTorch. Okay, so in order to do that, well, we first start by defining scalars, which can be tensors too. It's not the most convenient way of defining scalars, but we can do that. So we define a one-dimensional tensor, well, actually zero-dimensional tensor really, of size 1, and we define it to be 3 and 2, and then we can go and multiply them, and very unsurprisingly, this is, 3 plus 2 and 3 times 2 and, 3 divided by 2 and 3 to the second degree. Okay, so, well, as you would expect, this is high school math. Well, now we can go and define vectors. Vectors are basically a bunch of scalars. So a one-dimensional object with 4 entries, so vector 4 dimensions, sometimes people call that. There's some confusion because in d dimensions, and we just have standard vectors, right? Let's say in 3-dimensional space we talk about vectors are 3-dimensional, but sometimes people might refer to tensors also in terms of dimension, sometimes in terms of rank. There's a little bit of looseness, so just be careful when you look at that to make sure you understand what the other person is trying to explain to you. Anyway, so here's a vector, and it has 4 entries. And if I want to index into the entry on the 3rd position, I just do exactly that, right? And I index it just like I would in NumPy, and it will give me that entry. Not very surprisingly, I can ask, well, what's the length of it? But what's more interesting is I can also create a shape. So the shape in this case, well, also gives me 4, but it gives me that as an array, and that already indicates that sometimes maybe I may get more than just a single number here as the answer. As a matter of fact, for instance, when we go to matrices, we'll see that we'll get, 2-dimensional, well, 2 numbers in here. And so, matrices. So matrices are essentially vectors of vectors, if you will. And here's how you typically might write out such a matrix, A11 up to AMN. And if you've ever used a spreadsheet, well, or if you watched the data frames tutorial from before, essentially these are data frames or spreadsheets where all the entries are of the same type. And so I'm going to create a 5x4 matrix. I'm going to do that by creating numbers from 0 to 19 and then reshaping it to be a 5 by whatever's left over, and then I'll go and print the matrix and its transpose. And transpose is really just taking the matrix and flipping it over, right? So think of this as taking your matrix and then flipping it over, right? So you flip. Anyway, this is what you get, and you can see that first we went from 0 to 19 rows first, and now we're going from 0 to 19 columns first. Okay. So a special type of matrices are where things match, and like this. So this is called a square matrix. And now there are very specific square matrices, such as symmetric matrices. So these are matrices where the entries of the matrix equal the matrix transposed. Let's just print that out. So this is a matrix 1, 2, 3. Here we have matching entries. There we have them as well. There as well, and there as well. By the way, there's an antisymmetric matrix where the matrix transpose is the negative of the matrix. So let's see whether we can construct such a matrix, right? So obviously on the main diagonal I cannot have any non-zero entries because only 0 is minus 0, right? And so now we need to flip these terms. Here we get 0, and then we can check whether that's true. Okay, so now it's an antisymmetric matrix. Okay, so let's then go beyond 2 dimensions. So, well, I can simply take a tensor of, so basically a vector of size 24 entries, and of course 24 equals 2 times 3 times 4, and I can reshape it this way. By the way, I could have also done this, right? And it would have worked just the same because obviously I don't really need to specify the last dimension. This just simplifies my life a little bit. Obviously also if I were to try this, it would end up in tears because, as it already says, only one dimension can be inferred. So let's put it back to that. Okay. Now I can do all the useful things with a tensor that I could have done otherwise. Namely, I can, clone them, I can add them together, and so yes, if I have a, tensor, in this case it's a matrix going from 0 to 19, and I make another clone of it, and I sum it up, then these entries are going to be twice the entries from above. Okay, well, that's very unsurprising, but I can do more interesting things. I can multiply matrices. And there's a really, really important thing, and this is a perennial source of bugs in code, especially if you're a beginner. A times B is not a matrix-matrix product. A times B multiplies the entries of A element-wise with the entries of B. So the result of this is A11, B11, right? And since A and B were the same, going as numbers from 0 to 19, this is the number of entries. These are all the squares, right? So if I were to do this, I should see the same answers in both cases. Okay. Now I can add things, right, and multiply them with a scalar. All those things will work. Broadcast will work. So all of those operations will work just fine. So A plus X and A times X, they're, in both cases, tensors of, third rank. And so if I look at the shape, nothing's changed. Now, one interesting thing I might want to do with those tensors is I might want to change their shape. For instance, I could decide to sum all the entries. When might I care? Let's say these are, deviations between the image that I'm observing and the image that I'm predicting. Then I might want to take the difference, square it, and sum up all those terms in order to find out how well my algorithm is doing. Okay. So in this case here, we just have a vector from numbers from 0 to 3, and then I can go and sum it all up. And very unsurprisingly, 6 is the sum of 0 plus 1 plus 2 plus 3. We can look at the shape of matrices, we can sum it up, and again, what happens is, as expected, initially we have a 5 by 4 matrix, and then if we sum everything together, we have a scalar, and the entries sum up to 190. Okay. Now, sometimes you might not want to sum over all the elements, but maybe only row-wise or column-wise. And you can do that by specifying the axis. So you specify the axis over which you're going to be doing the summing. So axis equals 0 picks, that axis, axis equals 1 picks that one. If I have high dimensional objects, I can actually specify multiple axes, and we'll get to that in a moment. But for now, since, remember this was a 5 by 4 matrix, summing over the dimension that has, the 5 entries will leave me something 4-dimensional, whereas summing over the dimension that has, 4 entries will give me something 5-dimensional. Okay, which is exactly what it should be. So keep that in mind. And sometimes you might just do that to be defensive, to specify the rows, to make sure that it's really clear what you're doing. This sometimes makes the code more readable. Okay. Now, as said, if I want to sum over rows and columns, I can simply specify, axis is 0 and 1, and that would be the same thing as, axis, as sum. So if I were to do this, then I'll get the same answer in both cases. Right? Now, one useful thing that you might want to do, for instance, you have a long sequence and it's a machine translation model, and you look at the errors, and then you want to get the average error rate, then you might have to divide the vector of errors, sum it up and divide it by its length, and that's what we get here. So the mean will happily do that for you, or you can do the more pedestrian way by summing the entries and dividing it by number of elements. I strongly recommend you take the first thing because, well, C++ or CUDA is faster than Python, and so this way you are using a built-in function, and otherwise the Python interpreter has to do something. Now, of course, you can do that also coordinate-wise, and okay, we get that here. And so, yeah, if I compute the mean along axis 0, right? So this gives me, remember, we had, four entries on the remaining directions. So this is, computing the mean over the the first axis, right? So that was the one with 5 entries. So we get basically 4 numbers back. And by the way, of course, sum axis 0 will give me the same thing. And so this is really a shorthand for that. But again, use this because it's faster. Now, in some cases, what you may want to do is you may want to keep back the information about which tensor the data came from. So this doesn't necessarily yield any different number of entries that you get, but it still keeps the information about where the object came from. So what I mean by that is, remember, we could also have a.shape. Let's just print that out for reference. So if you look at that, right, so we performed a sum over the first axis, and very unsurprisingly, the first axis now collapsed from 5 dimensions into 1. And okay, that's the output of it, right? Now, usually if I didn't have keep dims equals true, let's just see what happens, right? Then you'd only get, an object that only tells you that there is 1 dimension, right? But if I do the other thing, it keeps the information as to the fact that there was, another dimension here, and that everything has just collapsed. The reason why you would care is because you want that information for broadcasting. So if we want to divide, A by the sum over A, then it'll, happily do that if I keep the dimensions true. Otherwise, it's a little bit wavy. Okay. Now, obviously, if I do this, I end up with a matrix that's normalized to corresponding, well, column sums to be 1 each, right? And I can check that by invoking c.sum axis 0. That's exactly, the axis over which I computed the entries before, and I get all ones. This is, by the way, a rather useful thing that you may want to use. For instance, in the case of attention weighting and so on, you need to make sure that all your weights sum up to 1, and this will happily do this for you. Okay. But we'll get to attention much, much later in a lot more detail. Another useful property is the cumulative sum. So this basically, if you recall, this was A, right? And then here, this is just the running sum over the entries. And, well, again, axis 0 means the first row is unchanged. The second row here is now the sum of the first and the second row, so this is unchanged. Here it's 1 plus 5 equals 6. And then now the third row is the sum over the first 3 rows, and so on. For instance, if I need to compute a cumulative distribution function, this might be something that you will care about. Okay. Let's see what else we can do. Well, now we can do the interesting things that matrices and vectors and other things are actually known for. Namely, I can compute, for instance, inner products. So one of the most fundamental operations is to take two vectors, pointwise multiply them and sum them up, right? And this is exactly what I'm doing here, and torch dot dot will do that. So if I have two tensors, then, their sum is just that, right? So this is nothing else but torch sum of x times y. So remember, x times y was just a pointwise entry. So if I were to do this, then yeah, okay, it's the same thing. Now, let's see what else I can do. I can, for instance, compute matrix vector products. Matrix vector products sound like a really complex thing. They aren't. All they do is they just are essentially vector products, but I'm just doing an entire vector of those. So if you think about it, you can view a matrix as a vector of vectors, and thus the matrix vector product is just a vector of vector products, right? So this is MV, matrix vector. And okay, let's just turn off the camera so you can see all the entries. And they are, very unsurprisingly, the product between matrix and vector. And yeah, by the way, obviously, as always, thanks to Amazon AWS, that's where the D2L team works at. And so thanks to Amazon for providing us all the support to do this work. Okay, so again, if we look at this here, right, A is just, a 5 by 4 matrix, X is a 4-dimensional vector, and then, matrix vector will give me something 5-dimensional. Okay, and almost at the end, I can take a matrix product, and MM will do exactly that. So be super, super careful not to invoke A times B. Right. So A times B, let's just actually do this here, right? And what would happen is almost certainly that this will not work. And the reason why it doesn't work is because actually not even the dimensions match up, right? So, right, because A times B would try to pointwise multiply, and of course, the full matrix product isn't the pointwise multiplication. Okay. So just be very careful, because this is otherwise a ridiculously easy way of injecting errors into your code. Okay, last but not least, norms. Sometimes you might want to know how long a vector is, and the easiest way to do this is to simply call norm, right? And the norm, this is the Euclidean norm of this vector, is 5. Well, that's a very well-known thing. So this is something that actually the Egyptians knew when they had to calculate right angles in fields. They had basically a string with equidistant knots, and they had basically 3 equidistant spaces on one side, 4 on the other, and 5 on the other. And this would give them, by Pythagoras, a really nice right angle. And yes, this is what you can do to make right angles in a field in essentially, well, 2,000-3,000 years ago. Anyway, here we are into Euclidean norms, and well, torch norm will just do that. But sometimes you just care about the sum over the absolute entries. Sometimes this is also called the Manhattan distance because you have, streets and avenues, and you can usually not walk diagonally. Well, it's not quite true. There's also the Broadway, but if Broadway is far away, then yes, you really need to walk the appropriate number of blocks. And so if we do this, torch abs sum, abs computes the absolute values, then we get that. And then, of course, you can apply the, so to say, Euclidean norm also to matrices. And it turns out that it has a special name there. It's called the Frobenius norm. It actually has a couple of interesting properties, such as being, the sum of the squares of the eigenvalues and all of that. So this is kind of nice. It's basically the trace of the matrix times the matrix transposed. So it has a lot of nice spectral properties and so on. But if you want to impress somebody with non-existent math, you will talk about the Frobenius norm and then just get on with it and use it to keep all the entries in a matrix small. Well, don't do that because you look like a poser. So basically use names appropriately, but Frobenius norm is actually what it's used and for matrices. And so if we were to invoke that, we'd see that, yes, in this case, 4 times 9, square root of that is, well, 6, because 4 times 9 is 36, because we have lots of sums of 1. 1 squared is 1, and then square root of that, okay, so we get the length of 6. And that is the Frobenius norm. And with that, we are done for this lecture.